You ever look at your phone specs and see quad-core or octa-core and just kind of wonder, what does that even mean? Why do we all of a sudden stop talking about gigahertz and start counting, well, brains? Okay, let's get into it, because the answer is this incredible story about engineers hitting a literal wall, the limits of physics, and having to get really creative.
I mean, if you grew up in the 90s or the early 2000s, it felt like absolute magic, right? Every new computer you bought was just this massive leap forward from the last one. It was a golden age of speed, and honestly, it felt like the party was never going to stop.
But here's the thing. For decades, that incredible progress, it wasn't magic. Not at all. It was all running on a surprisingly predictable and simple rule. You could pretty much call it a law.
And this right here, this chart is that law in action. See that green line just shooting for the moon? That's Moore's law. It basically predicted that the number of transistors, the tiny little on-off switches that are the guts of a processor, would double about every 2 years, like clockwork. And for a long, long time, that was the engine driving everything forward.
The whole formula was just so beautifully simple. You cram more transistors onto a chip, you can crank up the clock speed, going from megahertz to gigahertz. Faster clock speed, faster computer. Easy, right? Well, that simple little party was about to come to a crashing halt.
So yeah, that incredible, relentless progress was about to meet its match. And it wasn't just one little problem that popped up. Oh no, it was a triple threat.
Around the mid-2000s, engineers everywhere started to realize that the simple formula of more transistors equals more speed was just broken. They were pushing up against the fundamental limits of physics. It's like they were flooring the gas pedal, but the car just wasn't going any faster. Something was seriously wrong.
And these were the culprits. The three big villains of our story. The memory wall, the power wall, and the instruction-level parallelism wall. Any one of these would have been a huge problem. But all three at once, they stopped that race for raw speed dead in its tracks.
Okay, so let's break these down. First up, the memory wall. I want you to imagine your processor is a world-class chef. I mean, this chef can chop an onion in a nanosecond. But what happens if it takes 10 minutes for someone to bring him that onion from the pantry? Well, the chef just stands there, tapping his foot, completely useless. That's exactly what was happening. The processors got so ridiculously fast, they were spending most of their time just waiting around for data.
Next, you've got the ILP wall. Okay, think about building a house. You can have plumbers and electricians working in different rooms at the same time, no problem. But you absolutely cannot put the roof on before the walls are up. Some steps just have to happen in order. It's the same with a computer program. Engineers got super clever at juggling instructions, but eventually you hit a hard limit. A single brain can only juggle so many things at once.
And finally, the big one, the power wall. This was the real showstopper. Pushing those clock speeds even a tiny bit higher started demanding an insane amount of electricity. It was like trying to get your car to go 1 mile an hour faster, but needing an entire extra gas tank to do it. And all that power creates heat, a ton of heat. So much that the chips were literally in danger of melting themselves.
And you want to know how bad it got? This number says it all. At one point, to get a measly 13% improvement in performance, engineers had to crank up the power by a staggering 73%. Let that sink in. That's not just a bad trade-off, it's completely unsustainable. You just can't build a future on that.
And this chart, wow, this chart tells the whole story perfectly. Look at that green line for transistors. It keeps on climbing, just like Moore's law said it would. But now look at that dark blue line for clock speed. Right around 2005, it just flatlines. It stops. All those extra transistors were no longer making the single brain any faster. The old way was over.
So what do? The entire industry had to pivot, and fast. If you can't make one brain faster, what's the alternative? Well, what if you just give the computer more brains?
And just like that, the entire philosophy of the industry shifted. The old goal, one single super fast brain with the highest possible clock speed, was thrown out the window. The new goal was to use all those extra transistors to build multiple, smaller, and way more power-efficient brains, or cores, all on the same chip. Here's the best analogy. Instead of trying to build one single skyscraper that reached the moon, which was becoming impossible, they used that same real estate to build a bustling city full of smaller, highly efficient buildings. It turns out multiple smart cores working together can get way more total work done than one overheating, power-hungry supercore. This was the birth of the multi-core era. But
And this is a huge but. This brilliant hardware solution created a completely new challenge on the software side. A challenge that, frankly, we're still wrestling with today.
Think about it. Having a team of 8 brilliant people is great, but if they don't know how to communicate or coordinate, all you get is chaos. It's the exact same problem with processors. You can't just throw an old piece of software at a multi-core chip and expect it to magically run faster. The software itself has to be totally reimagined.
You see, the old way of programming was sequential. It was like a recipe. Do step 1, then do step 2, then step 3, in order. The new way is called parallel programming. You have to break your big problem into smaller chunks that can be solved at the exact same time by different cores, and then cleverly stitch all the results back together. It's way more powerful for sure, but it is a lot harder to write.
And that really brings us to the big question today. The hardware revolution happened. We now have billions of transistors giving us these incredible multi-core chips in every device we own. The city of brains has been built. The challenge now, and for the future, is for programmers to become the city planners, to write software that's smart enough to actually put all those brains to work.